Go? We go now?
Yeah, we're going now. You start.
Hello, and thank you for coming for the most haphazardly organized papers we love ever?
Yes.
Ever. This is less than 24 hours from Inez freaking out about not having a venue to us having an event here. Humble brag. We made it work. We've had speakers cancel.
Yeah.
An hour ago, right?
Emergencies, yeah.
We're all here. Hopefully that person's okay.
Yeah, hopefully.
Thank you for coming. This is New Relics event space where we'll hopefully be having much more of these. I don't know how many people know or care. New Relics product engineering is mostly based in Portland, but as of like October, there's a team here that used to be Opsmatic. I was the CTO by default of that. Now I'm the engineering lead for that team. We are building a lot of cool new stuff, and I'm heading that effort up and just generally trying to use all the resources that this wonderful company has given me, including this massive event space. So look forward to more of these. Obviously, we're hiring. It's a great place to work. I'm super stoked. So check that out. And with that, I'll hand it off to our wonderful organizer, Inez.
Well, hello. Thank you so much for coming today. This has been an interesting journey. Next month, we have a meetup on congestion control, and that will be really good too. So just please come to that if you know what's good. So every time that is a new, it's a really good meetup. Yeah. So I tend to introduce the speakers by making something up about them because I feel that is fun and it amuses me. So we're gonna introduce Gilbert. So here it goes. Gilbert Bernstein is a PhD student in the Department of Computer Science at Stanford University. His work focuses on a range of topics across computer graphics, HCI, and programming languages, including domain-specific languages, visual tools for artists and designers, geometry, topology, and recognizing Taylor Swift in inanimate objects. He's gotten some awards in the past that you don't really care about, and the only song Gilbert can rap at karaoke is Amish Paradise. So let's give it up for Gilbert. Woo.
Thanks, Inez. Hi, everyone. I'm going to be talking about classic graphics paper, Marching Cubes. So how did I end up talking about this? Well, Inez asked me one time if I could do a Papers We Love talk. And I said, okay. But I didn't really know what I was going to talk about. I figured I should do something with graphics, because I think of myself as a graphics person, and there's always all these systems or PL or machine learning talks here. And there's a distinct lack of pictures. So I'm going to try and remedy that for you. But I didn't know what graphics paper to do, so I went to my computer, and I decided to just see, what are the most cited papers at SIGGRAPH, the big computer graphics conference. And I was shocked that Marching Cubes has something like 3 times as many citations as anything else. It's been downloaded about 3 times as much as any other paper in the history of the conference. It's not, one of these, oh, yeah, citation counts are a great way to figure things out, but this is like giant spike in those statistics. And to give some context here, there was a previous Papers We Love talk about the rendering equation, and that's like down in the normal famous graphics papers. This is sort of interesting. Hopefully I'll talk a little bit about why that's the case, or it'll become clear. But let's get started. In case you don't know, what is this Marching Cubes thing, and what does it do? Well, suppose you have something like a topographic map of San Francisco. Everyone familiar with these sorts of maps? Roughly? Yeah. OK, so it's showing us the height of the city at different points in space. So you can think of this as a function giving a scalar value the height to every point on the land. And if we zoom in and look at this, we can see there's all these lines that are used in this visualization. And these lines are called isocontour lines. For instance, this one right here marks off 100 feet of elevation. So, this is useful if you want to travel a fairly flat route on your bike or walking. And basically, what marching cubes does is it extracts the one-dimensional higher version of this that we'd call an isosurface. So a surface in a volume where all of the points have the same value in some scalar field. The reason why the researchers, Lawrence and Klein, came up with this is they were at General Electric Research in Schenectady, and there was a bunch of historic work there on MRI, and they wanted, and this is a CAT machine, this is an MRI machine, and you put a person through it, and you get slices of, say, their head, like this. And this is the sort of data that the doctor will look at. They flip through a stack of images like this, which are taken one at a time. And what these researchers wanted to do was give a slightly more useful version of it. They said, well, why can't we just reconstruct a 3D surface of, say, the skull, and then you could just see the whole skull at once, instead of having to be an expert to somehow reconstruct in your head all these slices. It's a pretty compelling medical visualization reason. But once you have it, you can start doing lots of visualization. So for instance, here, this is a fluid visualization of a simulation done at Lawrence Berkeley National Labs. And on the right here, you can see isosurfaces of value flux 0.005, whatever that means. And then over here, you can see multiple isosurfaces being rendered translucently over each other to give you a sense of what's going on in the whole simulation. So this can be a basic building block that you use to build up a scientific visualization. And if you're in the special effects industry, you probably also want to extract surfaces from volumes. So one very common way of modeling the water-air boundary in a simulation is to use something called a level set, so some scalar function over the domain, where it's going to be negative inside the water and positive outside. So then when we want to render it, we just pull out the surface. We can apply the same idea to do 3D sculpting. So we've got voxels that somebody sculpts, and we keep track of some function. It says how much we're inside or outside of some object. And then to render, we just extract that isosurface to display it. This is a 3D coat here. And this is the same idea if we want to do 3D scanning. This is sort of a standard-ish 3D scanning pipeline, where we might take something like a Connect or some other sort of source of producing this data, get something like a point cloud, convert that point cloud into one of these scalar fields over a volume, which says how much we're inside or outside the surface, often called a sign distance field. And then, as a last step, we extract a surface as a zero-value isocontour. OK, cool. And this gives you a good idea, more abstractly, why this is so useful. It's this one step that you can plug into a bajillion different pipelines to get you from one essential kind of data, volumes, to another essential kind of data, surfaces. So that's why this was a really big deal. It's sort of the first paper that was roughly in the right place, or had roughly the right approach to solving this problem. OK, so how does this whole thing work? Well, I'm going to illustrate it more simply by using squares instead of cubes, because I can draw in 2D better. So suppose we have our scalar function here that I've sort of plotted with some red and blue values. And we sort of presume that there's some surface underlying this that we want to get out. To simplify things, for walking through the example, let's just threshold everything to binary values and see what we get. So we take a little square that we start at the top, and we start scanning along. So the first square, everything's on the same side, right? They're all in. Do you want blue to be inside or outside? Inside. OK, blue's inside. So they're all inside the surface. But oh no, now one is outside, and we need to put in a surface there that separates the two. Makes pretty good sense. Since I'm just simplifying everything in binary, just assume it splits each of these edges in the middle. do likewise here, and we just march along. And of course, this is sort of the simplified case. This will get us the connectivity, the topology we want. But then we're going to interpolate these values for where these points lie on the edge based on how much continuously the 2 points on the end are inside or outside the surface. OK. So to make this work, we need to somehow deal with a case analysis here of what's going on for each square. And for squares, it's pretty simple. We've got 4 different vertices. They can be inside or outside, right? So we got 16 cases. There are those 16 cases. And these are mostly pretty straightforward. So we can see a bunch here where it just cuts off a corner, as well as some simple ones where it just puts a line through the square. But then there are these 2 cases that are a little bit nastier, because they have this sort of switching pattern on the vertices. And the issue here is these cases are kind of ambiguous, right? We could put in surfaces that way or the other. But it doesn't really matter which we do, so just pick one. And that's because really all we need is for these things to agree on the edges. So that's pretty straightforward. But when we go to 3D, this is a little bit more involved, because now you have 8 vertices, and so that's 256 cases. Oh, but you can build a cool case table in memory, right? And you got your 8 bits there, and you can index into it, and won't this be fun to engineer? So this is clearly attractive to people who really enjoy that sort of thinking. But there's still, this complexity of these cases. You don't want to go and enumerate them all. So in the paper, they said, there's these 14 basic cases, which collapse to from symmetry. And you should feel really uncomfortable with this if you have a good instinct in you. So this is one of my professors in undergraduate who taught a logic course, Dr. Alan Klein. And we were just proving things in that class. But he said something that I feel is the perfect comment on this. Which is, if you're trying to prove something by a giant case analysis, odds are you're going to get it wrong. And I think this applies to programming as well. So it turns out in this whole case analysis, the argument they use to back this all up fits in these nice 3 little paragraphs, and it's totally wrong. What's the problem? Well, it's a problem we just talked about, right? There's sort of this ambiguity. And you see this pattern showing up on the sides of all these cubes all over. And they don't really say what to do about it, right? And in fact, they even say, oh, case 13 is symmetric with if you just changed which of those vertices were labeled one way or the other. But it isn't really, if you care about the surface, right? So when you run marching cubes, vanilla marching cubes, you're going to get a bunch of holes in your surface. So it's one of the sort of essential problems with the paper. And people proposed various fixes and other sorts of tweaks on it. Maybe one of the better ones here is this notion of marching tetrahedra. So we're going to break up each cube into a bunch of tetrahedra according to the diagram up there. And now the tetrahedra are back down to 16 cases, and those are pretty well controlled. And you can enumerate those, and everything's cool. Oh, but now you get some weird bumps, so you have to do some more post-processing to deal with the bumps. And, well, then there's some other weird reasons that people kept coming up with different ones of these, like patents. So the marching cubes algorithm was patented. Great thing to do if you want to piss everyone off is come up with a fundamental algorithm and then patent it so everybody else has to futz around with other dumb shit. There's some more things I can say on patents, but ask me afterwards if you want. So for a while, there's just all these little fixes futzing around, but really sort of the interesting thing that happened was in 2002, people actually came up with a better idea. And this is sort of the one thing I would say everyone hopefully would know on top of marching cubes. It doesn't have anywhere near as attractive of a name. And they had maybe much less noble goals that they set out with when they tried to do this paper. So basically, I have a bunch of people, and they want to make a video game, right? Good reason to do research. So the idea of this is pretty easy to explain. You just need to know what those terms in the title mean. So Hermite Data is a fancy name for saying you don't just have a scalar field, but you also have the gradient of that scalar field stored in the data. So you sort of have these normals at every point as well. And often you can get stuff like this from scanning apparatuses. So this is super valuable. And if you don't have it, you can sort of fill it in from the underlying scalar field in some fashion. Just take like local finite differences. And again, we think of this as separating some surface with the zero contour. The second idea in the title is that you use the dual grid. And this is the brilliant part of this paper. So what do I mean by dual here? I mean this grid that's sort of offset and opposite of the original grid. So here's more precisely the notion. So in 2D, we have sort of our primal grid that's built up of squares or cells, edges, and points. And so we make points dual to cells, edges dual to edges, but going through the opposite way, and squares dual to points. In 3D, we have a similar thing, and we can think of that point as lying inside the cell, the edge passing through the face, and similarly as we go down. Cool? Okay. Here's the topology of the contour when you visualize it in the dual mesh. It's really simple. How many cases are there here? That's a very strong improvement over the rest of this stuff. The only problem you've got is it's doing this stair-stepping pattern. But I'm just showing it to you here with the binary data. So of course, if we have something more continuous, we can find those crossing points, just like we would before. But now we also have this directional data, right, this gradient. So we can interpolate that onto these points, which will give us kind of this local bit of a line, or in 3D, a local bit of a plane. And so we can do this for all of these crossing points. And you sort of already get the picture of what's going on here. Well, you figure out where to place dual vertices, which are now created one per cell, based on the intersection of these. And then you get your final surface out. There's a couple little fixes to this. You need to do a simple 3x3 linear system solve, which is literally something from high school mathematics, although you can read various books on how to do that more numerically stable. But that's basically the whole idea. It's very nice. So sort of to wrap up here, some thoughts on what's so great about these algorithms, besides the fact that they solve this problem, is one nice property is they have this small working set. And volumes can actually get quite large. Just consider 1,000 by 1,000 by 1,000, and you're already at 1 billion elements. So it's really nice if you just have to stream this stuff in from disk once when you're constructing the surface. And then you're going to get a much smaller representation. These algorithms are pretty simple to implement, which means you have lots of opportunity to optimize them, less opportunity to get them wrong. And of course, they're solving this fundamental problem, which is pretty good. So before I go, I'll mention one thing in this area that's an interesting, big open question. And this is courtesy Brian Curliss, who is a professor I know up at UW in Seattle. And to explain this question, let's go back to this picture I had of sort of scanning reconstruction. And what we talked about just now was sort of this last step, right? Extracting from the volume the surface. But one thing we didn't really get into is a question of how accurate that surface is a representation of the actual world that we tried to scan. And it turns out that we don't have a lot of good answers for characterizing that, especially when you start composing all these different pieces of this system together. As an illustration of this, this is one of my favorite recent papers at SIGGRAPH 2014. So this is one of Brian's postdocs. So they had this example where they took 4 synthetic scans of a totally flat surface with synthetic noise injected in, with the overlap here. So of course, in your reconstruction, you're going to see some noise, right? But the interesting thing is what happened in this overlap here, where you essentially now have more data. Does it get better? Does it get more close to flat when you add more data? And so in the technique they proposed, it does, in fact, because they keep track of information about the resolution of the scanned images that they came in with. But most algorithms that you would use, that most groups are using, will actually produce hyper-resolution. So you can see even more detail now that you've collected more data, which is, of course, totally spurious. And there's a great illustration of this notion if you don't have any idea characterizing sort of the fundamental signal processing properties of your system, you just start making things up. So that's about it. You can ask me any questions, and here's a set of links and references if you're curious about reading more or implementing any of this.
I have a mic, so if anybody has any questions. You do? You have a question? No. I thought you were looking at me. No. Nobody? Also, Gilbert has a talk coming up in 2 months, right?
Yeah?
Yeah. So
not on this, but yeah.
We don't know the topic yet, right?
No, probably space-time constraints.
Thank you for the talk. In the Hermite data, how do you actually determine the actual tensor fields for the surfaces? Like, how do you determine the directions for the actual vertices?
You mean like a normal on the surface that's output?
Yeah.
You can do a couple things. So you could certainly interpolate it from the underlying field, which is sort of what the Marching Cubes paper did. Sorry, I didn't get into this, but it's in the paper. Or you can always do it by averaging the nearby faces. That's sort of your go-to if you want a smooth surface that you do for. But ultimately, it's application dependent. You can reconstruct sharp edges with the Hermite technique, which Marching Cubes is very bad at. And so if you do that, then you also have this question of, well, do I want to make this sharp thing render as if it's smooth, or do I actually want it to be sharp? And it's hard to, there's not like an application independent right answer for that.
So it doesn't handle discontinuities very well, like in slopes and.
In which Marching Cubes or the
Hermite data set?
It does. You can. What I'm saying is you can actually reconstruct sharp features of objects from it. Which is sort of really weird from the signal processing perspective. That shouldn't be possible, right? Which is partly why I bring that up, right? You should be band limited on sort of the frequency of your surface, but it doesn't care. So.
Anybody else? All right. Thank you so much. All right, so while Caitie sets up, there's more food, there's more drinks, there's bathrooms on both sides. So if you need to, I will give you 2 minutes. So go ahead.
A+ on that slide quality.
Actually, I'm wearing it because I ran out of t-shirt after 3 weeks.
How much time are you here for? I didn't think you were Saturday. Oh, just Saturday. Okay.
How long? Saturday, I'm back. 3 weeks.
Sweet. Okay. Bueno, ya estamos. No era yo, fue el speaker. All right, everybody. Let's get going. So, all right. We're going to introduce Caitie, who saved the day today. Caitie McCaffrey is a backend Brad, distributed systems diva, and tech lover. I just grabbed your last thing and then just put Slade on top. So good. She focuses on web services, distributed systems, and maintaining a lifestyle blog that focuses on matching floral designs to your pet's mood. Caitie has a degree in computer science from Cornell University and has worked on several video games, including Gears of War 2, Gears of War 3, Gears of War 4, and more recently, Halo 4. She is currently the team lead of observability at Twitter. So let's give it up for Caitie. She's going to be talking about Sagas.
Hi. Is this on? Yes. Okay. Hi. So I'm going to talk about the Saga paper tonight. So I know I'm not the person who was on the billing originally, but I hope you find this interesting, even though, and it's great because now I know none of you have probably read the paper, so I can totally just lie if I want. This is me. Like Ina said, I'm a distributed systems engineer. I work at Twitter right now, but I did come from the games industry for a long time, and that's where I'm on the internet if you want to talk to me. I do that. But tonight we're going to talk about this paper from 1987 called Sagas. And it was written by Hector Garcia-Molinas, and I'm going to explain to you sort of like why I think it's interesting. And then we're actually going to go through like, this was written to be like on one database. It's actually a database paper. And then we're going to talk about like what it takes to actually make this distributed, because the paper doesn't, they say it's obviously implementable, but we'll get there. So first we're sort of going to go like, why are Sagas interesting? Like, why do we even want them? What motivated this paper? We'll go through the paper and like the idea in the paper, and then we'll talk about distributed Sagas. And then I'll briefly mention that we use it in Halo 4, but I'm not going to go through all of that tonight. So basically, like this idea, we used to build systems that were super simple. Like we had a website or an application that talked to our service that was just like horizontally scalable, and we had this one giant database that held like the canonical source of truth of all of our things. And we could rely on this database for things like transactions, and like that had ACID, and that we had durable, consistent storage, and we didn't really have to think about it because all our data fit in one database. So this gave us a lot of nice things. This gave us serializability in terms of consistency, and it also gave us ACID, which is atomicity, consistency, why am I blanking on I, and then durability, which I is basically serializability. Yeah, thank you. I was a jerk and didn't give myself any notes on this slide, apparently, because I used to have this whole thing memorized. But anyway, this is like a nice thing to have, and we wanted these things, and it's nice to program in this model is the whole point. Okay, but now we're in this world of like service-oriented architecture and microservices, or like whatever buzzword you want to call it now. But we don't have just like one service that controls everything in, say, our travel application. We have multiple services like that might control the car rental or the hotel reservation or your airline reservation. But like a travel agent or like, these travel sites are going to talk to all of those things to book you a trip. So the point here is that basically like we don't even have the option of one giant database anymore because like they're actually fronted by different systems, nor does all this data fit in one database anymore. So there's been a lot of research on different ways that we could sort of still live in this world of like ACID transactions and serializability. The first thing was sort of two-phase commit. And so basically, I'm going to quickly go through this. Henry Robinson actually has a really great blog post on two-phase commit if you want to like dive really deep. But the idea here is that in a distributed system, we'll have a coordinator that helps us coordinate and is sort of like a special leader in this. And they're going to say like, hey, I want to do this thing, which is like I want to book a trip, so I need a car and a hotel and a flight. So the coordinator will send, hey, I need you to do these things to all the different resources. This is the propose phase. And then all the resources vote whether they can do them or not. So like you would vote yes if you have a hotel room available, and you may vote no if like a car was not available that matched the user's criteria. So once all of the coordinators received all of the votes, if all of the votes are yes, it says commit, and then everyone will like execute the transaction, and so then you sort of see it all happen at the same period in time. And then if someone says, I can't do this, then it'll send an abort message, and all the resources will just like not apply the transaction. And then because we're in like a real system and asynchronous networks, you have to say done for the coordinator to know that everyone either got the commit or abort message. Okay, so there are some obvious problems with two-phase commit. Basically, you end up with O of n squared messages in failure cases when you have this like done that's not happening. And then like Henry's blog does a really good explanation of that I don't have time to go through tonight. You also have a single point of failure, which is this coordinator, so that kind of sucks. And then you also have like reduced throughput, right? Because essentially, while this action of I'm saying vote and like commit or abort and wait, these resources are actually like being held onto usually in the implementation by the individual service. So like if I know that I may have to like reserve this car, I'm going to hold on to that resource even though someone else comes in. And this can happen over a long period of time, right? It's not like the time request of one request. It's the time span of the whole transaction is much longer because you are like gated by the slowest component in the transaction. So that reduces throughput. And it has a lot of scaling problems. And it's also worth noting that none of the major cloud providers actually implement a two-phase commit protocol. Microsoft's Azure Cloud specifically calls out that they don't do it because of some of these reasons. Because it does not scale well at the order of like hundreds and thousands of machines in a database. So you also may be familiar with the Spanner paper. This was done at Papers We Love last year. So this is Google's globally distributed database. And this is a really cool thing, and they're trying to solve the idea of distributed global transactions. And they basically want to go and do this because they're Google, and they like can go and build this, and they have all these engineers. And this is also like a really important part of their business that they're able to maybe do these kind of transactions for very specific things. So the way they do this, and this paper is also very involved, and I recommend going and reading it or watching the Papers We Love talk, but the simple gist of it that I have time to tell you tonight is they do this with this thing called the True Time API. And then they also have GPS and atomic clocks installed on all the machines in the data center. So the True Time API, the other interesting thing to note there is that it's actually not even giving you like an exact measure of time. It's giving you a window of 0 to 7 millisecond latency average. So like actual coordination and like total ordering is not really even a solved problem with Spanner, but they just get the window very, very narrow that it's good enough for most cases. So Spanner is obviously expensive and proprietary. Like if you are Google and you can build out all your data centers and install this custom hardware, then like maybe that's an option for you. It's also worth noting that Google has fiber between all of their data centers, so they're also not going out over the wire, like over like the normal internet, like the rest of us. Like they have their own lines. So that also cuts down on some of the latency versus like if I was just going to call a service that happens to be running in Japan. That's going to be a way different latency than Google pinging its data center in Japan or wherever they have one, right? And then once again, like I mentioned, True Time API actually, like people think, like, the interesting thing about the Spanner paper is people talk about it like distributed transactions are solved, but I think it's like an anti-proof, and because it shows that like even with all of this stuff, we still couldn't get synchronization solved. We basically just got it down to be so small that it's like tolerable. So like I have a whole rant on this where we've basically like just assumed we've time bounded the problem because we know like the size of the globe is finite, but like this doesn't actually scale if you want to go into like space or anything. So it's like not a solved problem. Or we like colonize a planet that's bigger than the Earth, right? Like it just works because like we have actually a finite space. It's not a solved problem. That's another rant. We can talk about that at the bar if you want. So basically the whole point of going through two-phase commit and Spanner is that distributed transactions are really hard. And they're very expensive to even get something approximating it. And so like the idea here is like, can we do better? Like, can we have our cake eating to 2? Well, no, because we decided to build distributed systems and life is terrible. But like Sagas comes in and proposes an alternate solution and tries to give us a little bit of hope. So Sagas, this is like sort of the motivation behind it. I've talked about distributed transactions. I've talked about long-lived transactions. And this is a paper from the database community in 1987 by Hector Garcia Molinas and Kenneth Salem from Princeton. And they propose this thing of a Saga, and they define it as a long-lived transaction. So what they're actually looking at when they were trying to solve this problem is you have a single database, and I'm going to execute a transaction that's going to take a long time. And so it's going to hold locks on a lot of the resources in the database, and it's going to like totally like make my performance of my database come to a screeching halt. So they define it in the paper as Saga is a long-lived transaction that can be written as a sequence of transactions that can be interleaved. All transactions in the sequence complete successfully, or compensating transactions are ran to amend a partial execution. So what they're saying here is instead of having this long-lived transaction that touches a bunch of different resources and has to execute as one ACID transaction, can we break it up into smaller components, right? And so this is like what we're going to walk through here is they have, you have sub-transactions. So if like, you know, in our travel example, I was going to book a flight and a hotel and a car, and that was going to execute as one ACID transaction in a database, it would just actually be broken up into 3 different transactions. And you do this, and then the other interesting part is that you have this idea of each sub-transaction has a compensating transaction. And so compensating transactions are like how you can think of it how you would roll back the transaction. Except for sometimes when you execute a transaction, there's no way to actually like roll the state back to the same state as it was. Like what if the transaction was like sending an email, right? There's no way to actually unsend that email, like it's out there. But you can take a correcting or a compensating action, like sending a follow-up email to say like, hey, sorry, we got this wrong, like here's what's actually happening, right? And like we're gonna maybe give you a voucher or something if it's like a customer service related thing. And so the point here is that you have to think about failure and design a compensating transaction for every transaction that is part of your Saga. So like I said, C of n semantically undoes T of n. So it's like really important to understand that this isn't totally ACID. This isn't like a database is going to protect me from doing something that can't be undone. So you have to think about that if you're like designing and want to use Sagas. But what Sagas do give you that I think is really powerful is they give you this guarantee that either all of your sub-transactions executed and completed successfully, or when a Saga finishes running, some subset of the transactions completed, and then all of the like necessary compensating transactions were applied. So basically what happens is your database is back into like a similar consistent state or an equivalent consistent state than it was when the transaction started. So the thing that they're doing here and what they're really getting at is they're trading off atomicity for availability. So as you're executing each sub-transaction in a Saga, right, someone could see the result of that, and I'll walk through an example. So we no longer have the A in ACID. And this is because then I don't hold a lock on that object for longer than I need to. And so, or like if it's in a table or something that like needs to hold a lock to edit it, I can like have higher throughput and I'm not holding onto resources for a very long period of time for something that may fail or may succeed, but it's just, you know, reducing throughput through the system. And the other thing that I think is really cool to think about is like Sagas are a failure management pattern. I think a lot of people, or there's been a lot of talks and like blog posts on the internet where they'll write about Sagas as like the workflow pattern, and they're really not. Like it's not about workflow, and there's a bunch of different things that I think are slightly different that we can talk about later, but like the whole crux of this is like you have to think about when you're designing your application or these transactions is like, how do I want to handle failure? It forces you to think about what happens when something goes wrong up front, which I think is actually really powerful because not many things do that, and then like something goes wrong and you're like, oh no, all my implicit assumptions have just totally taken down my system. Okay, so let's walk through what it would look like in a single database. So this is like the travel application I'm going to come back to. So we're going to break it down into our sub-transactions, which is book me a hotel, book a car, book a flight, and then I can cancel the hotel reservation, I can cancel the car reservation, and I can cancel this flight reservation, right? And so like if I did all of these things and I applied all the compensating transactions, the travel database would be in the same state, right? The same things would be available. In order to make this work, they define this thing called an SEC, or a Saga Execution Coordinator, in the paper, and this is sort of like, this is going to do a lot of the coordination in the system. It is technically a single point of failure, but like it's not special in the sense that if it dies, another one can be spun up to take care of it. And then there's also a log, so they're going to log and write, this is on a single database, so once again we're using database transaction logs to do this, but they have an additional one. And so when you begin a Saga, you commit begin Saga to the log, and then you'll commit begin sub-transaction and end transaction, and then also if you have to abort the Saga, you'll commit those messages and begin and end compensating transactions. So that's how the SEC sort of knows like where in the state of the world everything is. It's going to go back to that log for the source of truth. So let's walk through what a successful Saga would look like. So if I want to go on vacation, I'm going to book a trip. I'll start booking the hotel. I'll do T of I. That'll complete successfully. So now like that hotel resource is held in my name. And the rest of the world can see this, right? If that was like the last room, no one else can book that. So this is where we're getting rid of atomicity in this like book a trip transaction. I'm now going to book a car rental. I now hold the car resource that completed successfully, and then finally it'll go and book the flight, and I now hold the ticket, and now like the saga has completed, and like I hold all of the resources, and I'm done, and I can go on my trip. Okay, so let's look at like what an unsuccessful saga looks like, just to prove that this works. We begin our saga again. I'm going to start to book the hotel. I'm going to get the hotel reservation, so if it was, once again, it was the last room, and someone else wants it, they're not going to have it, even though my transaction or my saga has not completed. I'm going to then go book my car, but like the car I want is not available for the dates I want, so that transaction is going to fail, and it'll like commit an abort saga log to the message, or to the saga log. And so at this point now I need to start the compensating transactions for what has already ran. So I start the compensating transaction for the car rental, so that'll release whatever resources I had held there in the system. Once that finishes, I can then go and start the compensating book hotel transaction. So that will just cancel my hotel reservation. And now that room is free for anyone else who wants to book it, even if they had just gotten an error message like a minute ago because I was holding on to it, right? Yeah?
So what happens if at the end of all this it says that you finally did?
It doesn't, because this is a database transaction, so it either succeeds or fails. I will get to the distributed problem. So remember, this is like what I'm walking through and what isn't described in this paper is actually a database log. So you sort of have this assumption that like the log and the SEC are tied, their failures tied together because they're on the same machine, right? So you don't have to think about this like, what if like async network gets there late? We'll get to that because the paper doesn't actually talk about that. I mean, it could like, and like just like in a database, like if the compensating transaction failed, like you would, and once again, in a distributed system, it's slightly different, but like, because this is a database log, it's going to execute the compensating transaction until it succeeds, right? So it's a transaction that will succeed on a database. The only reason it would fail is if the machine failed. Or I guess you could write a bad compensating transaction that would fail, and the paper doesn't handle you from writing bad code. It assumes you're writing something that doesn't like have a precondition that will fail in a compensating transaction.
You don't have another compensating transaction.
No.
And then keep building.
No, that gets super crazy. So yeah, it is making some general assumptions in the paper that they call it that you are writing something that essentially can always execute and be rolled back. Like if I held a hotel, then I could release it. Okay, so this is the thing that I think everyone was getting at. I'm totally gonna kill that thing. Sagas and distributed systems. So the paper literally says, due to space limitations, we only discuss sagas in a centralized system, although clearly they can be implemented in a distributed database system. Clearly, Hector Garcia Molinas. So I'll tell you a little story now. The reason I came across sagas is because when I was working on Halo, we were looking at how I was building the statistics engine. And we sort of had an actor-based model, but basically you could think of it as when you played a game with like up to 32 other players, we had to store all of your statistics and process them. And each player basically acted like their own service in terms of like how the API model worked. And so we had to ensure that basically like we knew when we had finished processing a game stat. And so we ended up looking at the Saga pattern for doing this. And so that was sort of like how I came across it. And we implemented a version. It's sort of like a roll forward, less interesting version because we didn't need all the bells and whistles that the Saga had. But this is where I got interested in distributed sagas. And so it's been something that like I've sort of worked on. So now we're totally diverging from the paper. And this is basically all just sort of like some of my work, and like I've talked to Kyle Kingsbury about this a bit, and like how we've like systems that have built this in the real world, but this is not like published. Okay, so SOA and microservices means that like we don't live in a nice single database world anymore, so we want probably a distributed saga, right? That would be great. So we can model this the same way, where instead of like having transactions, we have requests. So I would have like a book hotel request and a cancel hotel request and a book car request and a cancel car request, et cetera, et cetera. That maps very nicely. So a distributed saga is a collection of sub-requests and compensating sub-requests. Once again, maps pretty nicely, about the same. And then a successful saga looks basically the same way, right? Like if I made all these requests and they came back successful and nothing went wrong, then like it's good. So where it gets interesting is in the failure mode, but I'm going to go through really quickly the quick components. So we have a Saga logs like we did on our single database, except for now it needs to be durable and distributed for fault tolerance. So you can use something like Kafka or whatever. We used Azure Service Bus in Halo, but you can pick a log of choice. You need the Saga execution coordinators. This is still probably an independent service that's going to interpret and write to the Saga log, so it's the only writer. And then for an individual Saga. And then it's going to apply the Saga subrequests and apply a Saga compensating request when necessary. Okay, so it sort of looks like this, and this is not necessarily as pretty as the last presentation, but I don't do graphics, so this is what you get. So if we're going to start a Saga, our service is going to send like a book travel request. So the first thing that happens is all that information about the Saga is going to get committed to the Saga log as start Saga. And then at that point, you can respond successfully to the service that like, hey, this async process has started. At that point, the SEC will then start to notice that like there's something in the Saga log because it should periodically check. It'll see that there's a start Saga, and it's going to start executing a Saga. So what it's going to do is it's going to start executing the first transaction request. So it's first going to log to the Saga log that this has happened. Like that has to happen first before it does anything else. And then it's going to go and talk to the service that can like handle this request and say, do this thing. And then that thing is going to respond, and like maybe it did it, and that's fine. And then it's going to log that this has happened, right? And the reason I'm going through this so slowly is that we will get back to this, but at every single one of these arrows, like this can fail, and we have to deal with it. And it'll do the same thing for 2, and it'll log, and it'll do the same thing for 3, and it'll log, and then if it's complete successfully, you will get end Saga committed to the log, and then like should the SEC fail or something, you know the Saga is completed. Okay, so when do we apply compensating requests in this model? We can apply them if we get an aborted Saga response. This could literally be one of the services saying like, I can't fulfill that request because I don't have this resource. The start request fails. Like one of the requests that I'm doing in the transactions fails, or you can have an SEC crash in a non-safe state. So it can crash in a safe state, but we'll go through what those are, and you can keep going. So let's say we've gotten here, and service 2 says I can't do what you've asked me to, so it'll just say like no, and then the SEC will say, okay, I'm going to abort the Saga. So at this point, it's going to commit an abort Saga log to the message. And then what it'll do is it'll start applying the compensating transaction. So like start compensating transaction 2, and then it has to go back and do compensating transaction 1. And then once that finishes, it can complete the Saga. Great. What happens when compensating requests fail? So basically, if it fails, I need to be able to replay it again. So they have to be idempotent in this case. And that limitation was not imposed by the original paper. Another interesting thing, because it's an asynchronous network, is that they have to be commutative, right? Because I could apply the start, like do this thing transaction, like book the hotel. And if the delete gets there like first because of a timeout or something, it needs to be able to undo the thing that got done. It also needs to be able to sort of be like an identity as well. I don't have a good math term for that, so if someone has one who's better at reading papers than me, let me know. But basically, so like the compensating request has to be very special. So we've put a lot of limitations on this, which I think sort of depowers it. But in the real world, like when we're talking about microservices, it's not that bad. Because most like deletes in a RESTful service are idempotent and commutative sometimes. Depends on how they implement it. Okay. What happens when the Saga execution coordinator fails? So we have this log that's independent of it, so that has the state of what has happened. So safe states are basically when we spin up a new one to take its place, which could happen in seconds, depending on how your architecture is happening, or microseconds. You basically, if all the executed subrequests are complete, like you have a start TI and end TI pair in the log, then you know you're in a safe state, because there's no like outstanding requests that we don't know what happened to them. If a Saga has been aborted or processed with compensating transactions, then we also know we're in a safe state, and we can just continue applying compensating transactions. Unsafe states are when you have a start TI logged but no end TI logged. So at this point, you have to start up the SEC. It'll read this, and it has to abort the Saga and start applying the compensating transactions. And the reason this is because we've placed no limitations on these transactions that we're executing as part of the Saga. So like you can't replay it. You don't know if it's safe to replay. So basically what this gives us is request messaging semantics of our subrequests have to be, or can be at most once delivery, and our compensating requests have to be at least once delivery semantics. Our systems have to support this. But then, once you do these things, you end up in this nice world where, once again, if a Saga has completed, I know either all of my transactions or requests have completed successfully, or I know that some of them have, and all the necessary compensating transactions have completed successfully. So this is still kind of a nice world because it gives us this model of thinking like we did with a transaction, that we like end up with our system in a consistent state. All the resources that we try to acquire while doing this thing are freed. And so that's actually pretty powerful because you like have a definitive start and end state instead of just having all these loose ends in the air. Okay, so right, we just went over distributed sagas. That's like we need a distributed durable Saga log. So that's very equivalent to the Saga log in normal one database ones. You need an SEC process. And then your compensating request must be idempotent and commutative. So that's like sort of the extra that needs to be enforced to make it work. Yeah?
What happens in the case where the start transaction goes to the SEC?
Yeah.
And then the SEC responds and the response is dropped?
Which one?
So you say start Saga.
Yeah.
And you send a request to the SEC. Does the and I assume the SEC has to respond back, right?
It can. I mean, so.
I'm just wondering if you ever end up in a case where your log has like start Saga, start Saga, start Saga.
So start Saga is being written by the service. That's the only one who, like, the thing that puts the work on the queue.
If it sends out and it times out, but it was actually written, and then the service sends it again, wouldn't you potentially risk of having two start sagas next to each other in the log?
Yeah, so the start saga isn't idempotent.
Okay.
Right, so I'm not saying this is this
so
start.
There may be some saga that just stays open forever.
Well, it would start because an SEC would, like, if it got logged. Okay. It's an async transaction, right? So like you could so the point he's making is the start Saga message from like my service to the Saga log happens, but maybe I don't get a response because networks are terrible. So I actually have no idea whether my message was logged or not. And because we have not made any claims about this service to like logging the start Saga log as being idempotent, you can't replay it. You probably could devise a system, and I actually haven't thought about this problem a whole lot, where like if you send an ID, something that's like a unique ID, then you could make that request idempotent and know that it's already in the log, check if it's already there and in process. But that's just like my first thought. I haven't really sat down and thought through that one a lot. Yeah, Jordan. Yeah, that's probably a bad arrow design. Yeah, so you could probably do, I mean, there's no, the way we implemented it is we had something polling and watching the log to see what's there.
I think the arrow was what made it confusing.
Backwards,
when
yeah.
When it was polling, it's a lot more clear that even if that message is dropped eventually.
Yeah, the slide's not great. I should fix that for like the next time I'm asked to do this talk on like 10 minutes notice. Yeah, no, you're totally right. Yeah, so basically we're at the end, so this is fine. So we talked about the processes, we talked about these like extra limitations that we've now put on Sagas that are not called out in the original paper. And then now we have like, just to remind you, like Sagas are long-lived or distributed transactions. This actually works really nice if you had something that was like even long-lived in a single database. I think the example they give in the paper is basically like if you're running like some financial process at night, you need to scan the whole database, then like this is nice because you can just do things and then roll them back and you're not holding a giant lock on the table. So basically we're making the trade for atomicity for availability, so we are giving up things here. This isn't like beating any kind of CAP theorem or consistency stuff. And I think why I think Sagas are really important is it is a failure management pattern, and like there aren't many tools out there that help you think about and manage failure from the get-go in a design, especially in a distributed system. I think it's really great to have to think about like, well, if I send this request, like what happens when it fails? Like what do I actually even do? And have to build that in from the get-go. So yeah, that's all I have. If you guys have questions, I'm happy to take them now.
And I have mics. Okay, who wants a question?
Thanks. So quick clarification. SECs, there can be a lot of them in the network?
Yeah.
Okay.
You have to have some way then of coordinating like that only one starts a Saga at any given time. So you might need some kind of consensus system to do that, but not necessarily like you could, that's an engineering solution, right?
Has somebody written an SEC?
Not a generic one that I know of. I have written one in an actor. I actually like this model a lot with the actor framework. It works really nicely for message passing. So that's what we did in Halo with Orleans for some things that needed this strong level of stronger levels of consistency. Yeah, Jordan.
So like just the regular transaction like T1, T2, they also technically have to commute then, right? So that they can commute with, okay.
So it has to be commutative with
So
like
you're talking
T1.
about delete, you're talking about like, oh, I write like a doomstone or something,
Right.
so if a write gets there before or after the tombstone wins. Okay.
So it's basically like one of those things like the tricky thing is like if you have synchronous networks, not a problem, right? Actually don't need to solve this, but we don't live in that world. So if you have async networks, like you can basically have a timeout, right? And so like I don't know if T1 ever finished, and it may show up at some point later. So like those two operations need to commute. So I should probably like update the thing to say that it needs to be commutative. This is actually something that like when the first time I gave this talk, we hadn't fleshed that totally out, and then Kyle Kingsbury and I started talking about it more, and we're like, yeah, this is like a property you have to have.
I was told I can't ask about concurrent Pascal, so I won't. What I will ask is, I'll be the PL troll in the room, and I'll say, how do you guarantee that somebody writes something that's commutative and idempotent?
You can't. So you can't. We're putting a lot of burden on the developer to get this right. I mean, like, I'm sure maybe you can if like there's some PL way you can, but like I'm not enforcing you to use any language doing this. So like we wrote this in C# and we 100% did not enforce this except for through writing code that was designed to be idempotent and commutative. I know. This is a fair question because like basically like all the conversations we've been having have been like, we'll buy you like failed us in this way where like you can basically write crap code that like doesn't hold up to the properties, and that was me saying that, so he's just giving me my own argument back. Yeah, Tyler.
So first I want to say thank you, because when you said that you were going to do this talk at the very last second, I was at work trying to cobble together something for Inez at the very last second. So thank you for not making me do that. When you were talking about the ways that the SEC can fail in unsafe manner,
Mm-hmm.
you talked about then having to roll back the entire transaction when like you have a start like TN, but not the end TN. But couldn't you just roll back the last one, like attempt to roll back the last piece that you have and then roll forward from there?
Yeah. So you totally can. The paper actually goes into, that I didn't go through, it has a different thing called like forward recovery, where like say there's, and Halo stats was actually more like this. There was never a case where we were like, oh, I failed to process your stats, like drop them on the floor. That wasn't the thing. So we always forward recovery rolled, and so you could just say, and if you want to forward roll recovery in this, then like obviously your transactions have to be idempotent, your sub-transactions, because you have to be able to replay them. But then you don't really need commutative ones. Or like they talk about partial rollback and then roll forward in the paper, so you could totally do that. This is just the basic one.
More questions? Oh, Alex, no? All right. Going once, going twice. Sweet. Awesome. We ended.
We made it.
There's more food, there's more drinks. Help yourself. Yeah, thanks.
No, we're going to start slowly cleaning up. We're not being passive aggressive. Hang out for probably like half an hour, 45 minutes safely. And then when you actually need to leave, I'll just say that. So, yeah, enjoy yourselves. Don't mind us slowly putting things away. Thank you for coming.